Lecture of the series on uh, probability and statistics for AI. Today's, can people mute your mic, please? Everybody, please mute your mic. And I also very strongly encourage that you place your questions in the chat box. Do ask a lot of questions, okay? And comments, if any, and place them in the chat box. Now, we'll begin the third lecture of this series. This is on Z-score and start of in-depth discussion on central limit theorem, which is called one of the crowning glories of probability, the CLT of the central limit theorem. But before proceeding further, I would like to wish everybody safety and good health on this occasion of Ganesh Chaturthi. Please do stay safe and healthy. Now, this lecture will be technical. Okay, it will be technical because we'll go into some mathematical details, looking up tables, solving a problem, and all this is towards our progress towards test of hypothesis. Let me just remind you that all this discussion is inspired by the fact that we want to make claims about a population. And in this case, our population or our world is language. Okay? We are doing natural language processing and our world is language. Like the real world and many other worlds, this world also is full of extremely interesting problems, full of very challenging situations. And there is uncertainty in this world because language is the other name of language is ambiguity. And to deal with ambiguity, uncertainty, we need the instrument of probability. Okay, this is the motivation for the whole series. Let me also remind you of the style of our discussion in these meetings. We go extremely slowly, leaving nothing ununderstood. So all kinds of questions, foolish questions, intelligent questions, everything is welcome, and also welcome. So what we did in the last two lectures is that somebody's mic is not muted. All of you, please mute your mic. So two main ideas are conveyed from the two lectures. One is the trade-off between risk minimization and resource utilization. Okay, the trade-off between risk minimization and resource utilization, which is where we describe the bridge problem. So city authorities have built a bridge and they want to know how many cars can be allowed on the bridge. And the next problem was that of interval estimate, and we wanted to find out what is the percentage of sand particles which fall within a range. And that range is important for painters, for example, painting industry, which have to make use of sand particles for their business. So these were the two main ideas, and here we want to do some nitty-gritty technicalities. Now the bridge problem was that there is a bridge, and the bridges and the cars are on the bridge. We want to find out what is the safety limit for the number of cars which can ply on the bridge at any point of time. So we want the number of cars that will cause the probability of damage to the bridge to exceed 0.1. So what is the safety limit from the bridge for the bridge is cast into a question involving probability. What is the number of cars that will cause the probability of the damage to the bridge to exceed 0.1? Okay, there's a probabilistic casting of the safety question. The red text on the screen. My screen is visible to everybody. There is a red text on the screen. Can somebody verify?
Yes, sir.
Now, when does the bridge break? That condition is very simple. When the total number of the total weight of the cars on the bridge exceeds the tolerance limit. Okay. This is a very simple inequality, very intuitive. But to apply this intuitive situation, we need a formal framework, and probability gives us that opportunity. It facilitates that particular operation. So the tolerance limit of the bridge is known to be normally distributed. This is a tremendous piece of knowledge. Okay, we take it on the face value, and we take it for granted. हाँ ऐसा तो होना ही था, but not so. Okay, the fact that this is the underlying distribution is normal may not always be the case, as we'll see in the sand pile problem. And a guess at the distribution, underlying distribution, is a crystallization of a lot of observation. It is a piece of wisdom, piece of knowledge, which has been gathered after looking at a lot of data. It is a crystallization of experience into a piece of wisdom. Okay, so underlying distribution having a particular property is obtained after churning a lot of data and analyzing a lot of data. Similarly, the total weight on the bridge also happens to be normal. That is also an interesting fact. Okay, and what is the underlying mathematics or technicality involved? The total weight is the sum of the weights of the cars. And again, from the observation of data from our experience, it has been told to us that the weight of each car is again normally distributed. Okay, so maybe the situation is somewhat artificial, maybe a bit too simplistic, but not very far from reality. Now, since W total is the sum of W1 to Wn, where n is the number of cars on the bridge, what is the mathematical machinery available to us? Well, the mathematical machinery is the central limit theorem. Okay, central limit theorem has been invoked here, and we'll spend some time dealing with central limit theorem, which I said is an extremely important contribution from probability. So this total weight is again normally distributed. Okay, and what are the parameters? The parameters of this normally distributed quantity is that its mean is the sum of the means of individual variables, and and the variance is again the sum of the individual variances. So each card happens to have a normal distribution with respect to its weight, with the same mean and same variance, same sigma square. Okay, and then we can apply central limit theorem and say that the mean of W total is n into mean, and the variance of W total is again n into sigma square. Okay, this is known from our knowledge of central limit theorem. Now we can compare the two probability distributions and come to a conclusion about how many cars can safely be on the bridge. Okay. So this involves dealing with the mathematics of interval estimate. Okay, interval estimate. So point estimate versus interval estimate is again an important question in probability. And we have to deal with this in NLP machine learning situation many times. Interval estimate is important for us, as we'll see. So since we are coming to the question of interval estimate, we go back to our sand pile problem. Okay, it is a pile of sand grains obtained from fragmentation of a mineral compound, and we ask what is the percentage of sand that falls within a range, let's say from 2 to 3 units. This particular range is important for the painting industry. For the purpose of paints, for example, sand particles should be in a range of sizes, and there is a real life need situation, because these mineral particles are used in painting industry, also in plastics and paper, we are told. So now here comes here comes science. Okay, here comes science. We'll come to science, but we look at a similar problem where we want to estimate the percentage of people in Mumbai who are employable as construction labor. And the age range, which is legally allowed for construction labor, is between 18 to 58. Okay, and as we have said, you may get tired of hearing this again and again. We can always pick up every person in Mumbai and record their age and ultimately get the percentage of people in Mumbai who are employable as construction labor. But this is impractical, and dealing with this situation requires invocation of probability. Now, the problem statement with respect to the sand pile, we leave with that for a few minutes before going into technicalities. We have collected 10 grains from this large pile and we have recorded their sizes 2.2, 3.4, and so on, going up to 1.9. Now we want to estimate the percentage of sand grains in this entire pile, and their size should be between 2 and 3. So here comes science, which is beyond our current discussion on technique, computation, distribution, etc. Okay, we know from the work of mineralogists that the size of particles resulting from fragmentation of mineral compound has a log normal distribution. Okay, so this is called Kolmogorov's law of fragmentation. Kolmogorov, you remember, has also contribution in complexity theory, Kolmogorov's complexity, which refers to the size of the program that executes an operation. Now, the size of particles resulting from fragmentation of a mineral follows log normal distribution. This is a very nice piece of distribution, and we could not anticipate it. We could not anticipate. And this we know from looking at a lot of data and the behavior of these minerals. Now, what is a log normal distribution? The random variable x has a log normal distribution if log x has a normal distribution. So y is equal to log x. Fy is the probability density function. So Fy has this form 1 by root 2 pi into sigma and e to the power y minus mu square divided by 2 sigma square. So here mu is the mean of the normal distribution. Sigma square is the variance. Sigma is the standard deviation. So the variable x is such that the log x has normal distribution. Now, we can take this naive approach to solving the sand particle size problem. We remarked last time that we record the number of particles which fall in this range 2 to 3. And looking at the observations, we find that 4 sand particles out of 10 fall in this range. Okay, so then in this case, our estimate for this percentage is 40%. And we would like to call this naive. This is a very common operation that we do. If we toss a coin 10 times and get 4 heads, we would say that the probability of finding a head is 40%. So that has validity because the underlying distribution is Bernoulli binomial. Okay, but in this case, we know that the underlying distribution is not a multinolly multinomial. Okay, we know that. And when we are taking the ratio of these numbers and estimating the percentage of sand particles in the range 2 to 3, we are making a mistake. Okay? We are ignoring the underlying distribution in this case. So we would like to be close to reality. The reality is that the underlying distribution is not multinolly, it is log normal. Okay? The sand particle size follows a log normal distribution. So size of sand particles is log normally distributed. Computing with ratio of counts assumes multinomial distribution, which is not correct. Okay, so we have will remark on this, on this situation many more times as we proceed with the discussions. So here, let me digress a bit for 2 minutes maybe. When we do part of speech tagging, then if we apply hidden Markov model to get the best sequence of part of speech through the Viterbi algorithm, then the whole algorithm is controlled by two parameters, the transition probability and the observation probability. So we are interested in probabilities like what is the probability of a noun preceded by an adjective. Okay? So that we compute from the data by observing how many times noun is preceded by adjective and divide this number by the number of adjectives. So are we correct in computing the transition probability parameters this way? We are making an assumption about the distribution of nouns, adjectives, adverbs, verbs, prepositions, etc. We are making an assumption, okay, and that assumption is this multinomial, Bernoulli, binomial kind of situation. So we would like to talk more about it when we take up NLP problems. Okay, so now if we know the distribution, we must use it. Okay, that is the point. In this case, we have this knowledge that sand particle size is log normally distributed. I saw a chat. I saw a remark by Prince on the chat box. I'll come to that after some time. Now, if we know the distribution, we must use it. But how do we use this distribution? Okay, so that is the main theme of today's discussion. Okay, how do we make use of the distribution? Now, here we have to be looking at a very, very important concept called Z-score, which is the main topic of discussion today. Let me explain Z-score. Z-score comes from what is called standard normal distribution. Okay? And standard normal distribution is a normal distribution. It's a Gaussian distribution with mean equal to 0 and variance equal to 1. Okay, and this is a very, very important and useful concept. It is widely used in many different domains of activity in economics, statistics, of course, social sciences, mechanical engineering, civil engineering, everywhere. We find use of standard normal distribution whenever the situation demands use of probability, finding out interval statistics, test of hypothesis, and so on. Okay? So standard normal distribution has a bell-shaped curve with mean at 0 and standard deviation 1. Okay, standard deviation 1. Now, the area under the normal curve gives rise to what is called the Z-score. The Z-score refers to area under the normal curve, standard normal curve. Okay, so let's remember this carefully and kind of print it in our mind that Z score is an area, okay, under a normal curve, and a very special normal curve, the standard normal curve, whose mean is 0 and standard deviation is 1. Okay, so Z score corresponds to the area under the curve from minus infinity to Z. So capital letter Z is the random variable and the value is small z. You remember the convention, the random variable is always given a capital letter representation and its value, if unknown, is given the corresponding small letter representation. So capital Z equal to small z. So the area under the normal curve going from minus infinity to capital Z equal to small z is the Z score. Okay, let's remember this. And this area is also the probability value, the probability of the random variable Z taking value from minus infinity to Z. Okay, so this is the semantics of the Z score, and we would like to remember this very firmly and clearly in the mind. Okay, so Z score is useful for many things, and we'll take some examples. Now, a question that may arise is that, well, the standard normal curve is a very special normal curve. It's a very special distribution. It has mean 0 and standard deviation 1. But in real life, we are not encountering situations where mean is 0 and standard deviation is 1. The point is that any normally distributed random variable x can be converted to standard normal form by this operation. If z is equal to x minus mu divided by sigma, then you get the standard normal variable. So the operation is to subtract the mean and divide the result of subtraction by standard deviation. So this looks intuitive. Okay, you are dividing the distance by the standard deviation, but there is a little bit of technicality and mathematics involved in this. We would also clear this up if in some lecture. Okay, uh, this is intuitive. Okay, it is intuitive. We are subtracting a constant from a normally distributed variable, and you are multiplying it by sigma, by 1 by sigma. Okay, so a normal variable, uh, in normal for a normal variable, if you subtract a constant from it and if you multiply it by a constant, do you still remain normal? Okay, that is a question which is not really obvious, whose answer is not really obvious. Okay, so this needs a proof, and we would like to prove it by using what is called moment generating function. Okay, moment generating function. Let's remember this. We'll devote a lecture to understanding moment generating function. So there is a one-to-one correspondence between moment generating function and the distribution function. Okay, if you know the moment generating function, you can find out the distribution function and vice versa. So let's be clear about the terminology, and we'll make use of MGF, moment generating function, to show that 1 by sigma, 1 by sig, yeah, 1 by sigma into x minus mu is also normally distributed with mean 0 and standard deviation 1. Okay, so this looks intuitive, but it needs a proof. Do remember this, and remember this as an agenda. So from this discussion, we can really compute an interval probability. So suppose the random variable is z, and it can take value a and b. Then within this interval from a to b, we can compute the area, and we can get the corresponding probability value. What is the probability value? We are interested in the probability of the normal variable of the standard normal variable z being in the range A to B. And that probability is nothing but the area from Z equal to A to Z equal to B under the standard normal curve. Okay. This again, we have taken on face value, we have accepted this, but it requires a proof. Okay, maybe a very simple two-line proof, but we would like to establish that notion also. The fact that area under the probability density function curve from a point to another point indeed gives the probability of that random variable being in that interval. Okay. Also, we would like to go to the definition and establish. Now, the interval probability is this, and this interval probability is found out from the difference of cumulative probability. We'd like to become a little technical here, okay, and remind ourselves of the cumulative distribution function. So the area in the interval A to B can be found out by subtracting phi A from phi B. So what is phi A? Phi A is the area under the standard normal curve from minus infinity to A. and phi b is the area under the standard normal curve from minus infinity to b. So this is known as the cumulative distribution function. So it gives the cumulative probability, okay, which is obtained by integration from minus infinity to b and minus infinity to a. So the probability of the random variable z being in the range from a to b is nothing but phi b minus phi a. Okay, so this I suppose you see, you can accept it because two areas can be subtracted. Okay, that subtraction operation is allowed on the quantity called area. So the interval probability from A to B is phi B minus phi A. Now I would like to spend maybe 2 minutes on the difference between PDF and CDF, probability density function, and cumulative distribution function called CDF. Okay, so the PDF is denoted by PX and CDF is denoted by phi X. I don't know why this is not going. Okay. Yeah, it's gone. So, somebody please verify that you are seeing PDF and CDF on the screen.
Yes.
Yeah. Okay. Fine. So PDF is called the probability density function, and CDF is called the cumulative distribution function. So the relationship between PDF and CDF is that of integration differentiation. If I integrate the PDF probability density function from A to B, from minus infinity to A, then I get the CDF phi A. That is the area under the standard normal curve from minus infinity to A. Okay, so do be clear about PDF and CDF. CDF always involves integration of the PDF, and CDF is more useful than PDF because CDF gives me the probability in an interval. Probability in an interval. As we know from the definition of PDF, probability density function, that the probability at a point is always zero in case of probability density function. So since it is always zero, we are more interested in CDF, cumulative distribution function. So do please remember these quantities. And if you have any question on this basic, very fundamental, basic building blocks for our discussion, then please question on the chat box. Now, integration
The
of
person you are speaking with has put your call on hold. Please stay on the line. आप जिस व्यक्ति से बात कर रहे हैं उसने आपकी कॉल को होल्ड पर रखा है कृपया लाइन पर बने रहें The person you are speaking with has put your call on hold. Please stay on the line.
Yes, sir. We
आप
can hear
जिस
you,
व्यक्ति
but
से बात कर रहे हैं
I don't
उसने आपकी
understand.
कॉल को होल्ड पर रखा है
I think
कृपया
his voice
लाइन
would be
पर
more,
बने
but
रहें
kept it
The
on hold.
person you are speaking with has
I
put
don't
your call
understand
on
what is
hold.
this.
Please stay on
So,
the line.
I think the
आप जिस
owner of the
व्यक्ति
meeting
से
can
बात
drop
कर
that
रहे हैं
temporarily.
उसने आपकी कॉल
I
को
can't hear
होल्ड
you.
पर रखा है कृपया लाइन पर बने रहें
I
The
think
person you are speaking
Well,
with
right.
has put your call on hold. Please stay on the line.
I'll
आप जिस
reconnect.
व्यक्ति से बात कर रहे हैं उसने आपकी कॉल को होल्ड पर रखा है कृपया लाइन पर बने रहें The person you are speaking with has put your call on hold. Please stay on the line. आप जिस व्यक्ति से बात कर रहे हैं उसने आपकी कॉल को होल्ड पर रखा है कृपया लाइन पर बने रहें The person you are speaking with has put your call on hold. Please stay on the line. आप जिस व्यक्ति से बात कर रहे हैं उसने आपकी कॉल को होल्ड पर रखा है कृपया लाइन पर बने रहें The person you are speaking with has put your call on hold. Please stay on the line. आप जिस व्यक्ति से बात कर रहे हैं उसने आपकी कॉल को होल्ड
Hello.
Yes, I
I
think.
think now
Yeah,
should be okay.
yeah. Now it is good.
Okay, I'm back.
Yeah.
Yeah. Sorry. Share content. Yeah. So I was here. Okay. So can you see the normal expression formula on the screen?
Yes.
Yes. Okay. So probability of z less than v is minus infinity to v integration 1 by root 2 pi e to the power minus y square by 2. This is the standard normal form. Mu is equal to 0 in this case and sigma equal to 1. So it is difficult to find an algebraic closed form expression for this quantity e to the power minus y square by 2 integration from minus infinity to v. This is a cumbersome operation, and algebraic closed form expression is difficult. Okay, so what people have done is that they have tabulated values under this integration from minus infinity to different quantities. Okay, and that has given rise to an extremely useful tool in probability and statistics called standard normal form table, or the Z table. Okay, Z score table. So you can consult the table for the values that you want, and these values have been found out numerically. Okay, so I'll now show you how to make use of the Z-score table, the standard normal form table. Okay, I request everybody to please mute your mic. Um, so we are interested in area under the normal curve for different values of the standard normal variable z. So let's first make use of this standard normal table for a particular question that we ask. Okay? The z-score table, by the way, looks like this. Okay, you have the z values tabulated in tabulated in row and columns. Tabulated in row and columns. So, for example, if I am interested in knowing the value under the standard normal curve from minus infinity to, let's say, 0.21 to 0.21, I think the values are really small. But if you can read it, then I'll go on the row. I'll go on the row for the first place of the decimal. So 0.21 is what I'm interested in. So 0.2 is the third row, 0, 0, 0.0, 0.1, 0.2. And 0.21 can be obtained by adding 0.2 and the 0.01 column. So if I add the row and the column, then I get 0.21. And in that cell, 0.2 row, 0.01 column, I find the value 0.5832. Okay, so the area under the standard normal curve from minus infinity to 0.21 is 0.58. Okay, so this is the, can people please mute your mic? I hear a noise from somebody. Okay, please mute your mic. Okay, so now we look at a very popular question that we have often seen in test of hypothesis or test of significance. And that will illustrate to us how we use the Z-score table. We have heard many times that we have heard many times the term 95% confidence interval. 95% confidence interval. Okay, what does that mean? Okay, so 95% confidence interval means that the probability in an interval being 95%, being 0.95. Okay, and we have heard that under the normal curve, approximately 95% of the area lies in the range -2 to +2. Okay, and it can also be generalized to any normal curve, any Gaussian distribution, between the interval -2 standard deviation to +2 standard deviation lies 95% of the area under the normal curve. Okay, so the 95% confidence interval is approximately -2 sigma to +2 sigma, and -3 sigma to +3 sigma, you have about the whole of the normal curve area. So to be more precise, we know that 95% of the area under the normal curve lies within plus minus 1.96 sigma. That's why I said approximately 2. So from plus and minus 1.96 times standard deviation, we have 0.95 probability. Okay, so this is the so-called 95% confidence interval, and it is used very frequently in hypothesis testing. So there was a question from Aman about if we have such tables for non-normal distribution also. No, not that I know of. Okay, but there are also tables for T distribution. But we'll talk about T distribution because in T distribution we assume that the standard deviation is not known. So we'll discuss that later. Okay. So now this 95% confidence interval you must have encountered many times in your ML, NLP, speech, computer vision, AI experiments. Okay. So what is the meaning of this 95% confidence interval is what we want to make our understanding pakka on. Okay. We want to understand what does it mean to be in 95% confidence interval. Okay. Which is frequently mentioned in hypothesis testing. But are we clear about what this interval means? And whenever you have used it, have we used it knowledgeably? So we would like to first verify that the area from minus 1.96 to plus 1.96 for standard normal curve indeed is 0.95. We would like to verify that using the standard normal table, the Z-score table. Okay, so let's learn this technique as to how to do this task. So we know that the area under the normal curve is phi b minus phi a, where the interval is a to b. Now, in this case, we are interested in the interval from minus 1.96 to plus 1.96. So we are interested in phi 1.96 minus phi minus 1.96. Okay, and we would like to show that this is 0.95. Okay. So this is the interval, and we have to refer to the standard normal curve, and we have to make use of the Z-score table. Now, what happens is that the Z-score table is often given only for positive values. Okay, the example that I showed on the screen some time back, it had both negative and positive values, but most of the time Z-score table is given in the positive range. Okay, from 0 to whatever value. It cannot go up to plus infinity, but from 0 to positive value. So what do I do if I have negative value? If I have to find out the area under the normal curve from minus infinity to minus 1.96, what do I do? Okay. Here, the symmetry of the normal curve comes to use. Okay, comes to use. So let's see that first. So phi 1.96 by consulting the Z table is 0.9750. Okay, we'll go to the table very soon. Now phi minus 1.96 is actually 1 minus phi 1.96. Why is it so? It is because of the symmetry. Okay, the area under the curve from minus infinity to minus 1.96 is exactly equal to the area from 1.96 to plus infinity. Okay, so because of the symmetry of the normal curve, it is symmetric around the 0, x equal to 0. So 1.96 to infinity is exactly equal to area under the curve from minus infinity to minus 1.96. Now area from 1.96 to plus infinity is 1 minus area up to 1.96, minus infinity to 1.96. So I can reuse phi 1.96. So phi minus 1.96 is nothing but 1 minus phi 1.96. So phi 1.96 minus phi 1.96, phi minus 1.96 is 2 into phi 1.96 minus 1, 2 into 0.975 minus 1, which is equal to 1.95 minus 1, which is equal to 0.95. Okay, so we have proved that the confidence interval 1.96 minus 1.96 to plus 1.96 indeed is containing 95% of the area, and this is indeed the 95% confidence interval. This is very nice, but the question now that remains is that how do you get the value 0.96750? So let me show you how to read the z-score table or standard normal table. So we are interested in 1.96. Okay. So do you see a red circle? Can somebody verify? Do you see a red circle?
Yes, sir.
Yes, sir.
Yes, sir.
And do you see some values in that red circle? What values do you see?
0.97.
0.9750. You see that. Okay, great. So 1.96 I read off from the z-score table as follows. I take the value of z and go down the row to discover where I have 1.9. Okay, I have 1.9 here. Okay, a shadowed line 1.9. And 1.96 is nothing but 1.96 plus 0.06. Now, plus 0.06 will come from the column. So this is 0.06. Okay, so 1.9 row and 0.06 column. In that cell, I have a value of 0.9750. So this is how the z-score table is to be read. Okay, learn this, and this is so useful to us when we do our job of AI. Okay, so 0.9750. So 0.9750 is what I have got. Now I am equipped to find out what is the value of phi 1.96 minus phi minus 1.96, that is the interval probability. This turns out to be 2 into 0.975, which is 1.95, and 1.95 minus 1 is 0.9. So this proves that the interval from minus 1.96 to 1.96 is indeed the 95% confidence interval. Okay. So this is very empowering. Okay, we very clearly understand what does 95% confidence interval mean. How do we use this? We use it in many important situations. The importance of 95% confidence interval is supreme. It is often used backward for many problems. So we know that z is equal to plus minus 1.96 in z equal to small z. That gives me 95% confidence interval. Now z equal to x minus mu by sigma. Okay, so z equal to x minus mu by sigma, and therefore it gives me values of x mean and the standard deviation if 2 out of the 3 quantities are known. So if I know these if I know 2 out of these 3 quantities, namely x, mu, and sigma, then I can find out the third quantity, which is useful to us. Okay, so that we will see in finding out the number of cars on the bridge which will make the bridge unsafe, okay, which will have a high probability of breaking the bridge. So this is the operation that we'll use, okay, this kind of concepts. So let's proceed, and we go back to the mineral sand pile problem, where we'll make use of the technique that we have learned just now. Our problem is to find out the percentage of sand particles which are in the range 2 to 3. So I cannot do anything with 2 to 3. I convert them into log. Okay, so x is the size of the sand particle. So I deal with log. So log 2 is less than or equal to log x. Log x is less than or equal to log 3. I want log x to be in the range log 2 to log 3. So now I have the sample size as 10. The respective sizes are 2.2, 3.3, 1.6, and so on. I convert them into log values. So 2.2 log of 2.2 is 0.79, that of 3.4 is 1.22. Notice minus 0.22 because 0.8 is less than 1, and the log value will become negative. So I have got these log values. What do I do next? I take the sample mean. The sample mean is 0.75. Okay, when I take these values 0.79, 1.22, 0.47, etc., I can get the sample mean as the total sum divided by 10, which comes out to be 0.75. And I can also find out the standard deviation of these values, which turns out to be 0.44. Now I can subtract the mean from the random variable and divided it by standard deviation, and I now am in the standard normal form space. Okay, so now I in the standard normal form space. So I do this on the left hand side of the inequality, or the lower end of the interval and to the higher end of the interval, and I get these values: probability of Z being in the range 0.13 to 0.80. So this would be 5.8 minus 5, 0.13 minus 0.13. This is nothing but 5 0.8 plus 5 0.13, using the symmetry of the normal curve. So this is 0.79, 0.5 plus 0.55 minus 1, which is 0.32. Now, is phi 0.8 indeed 0.79? Is phi 0.13 indeed 0.55? Since we are learning the use of Z table, let's see this. Let's see this. So 0.8, under 0.8, you have probability value of 0.7881, and the other value was let me see, 0.13. So 5.8 and 5.13. We're interested in this. So 5.8 is 0.78 and 5.13. How do I get it? I get 0.1 from the row and 3 from the column. Okay, 3 from the column. So this is 0.55. So this 0.55, and the other value is 1.8. So I consulting the Z table, I find 5.8 is 0.79 because it was 0.7881. We took 2 decimal places, 0.79, and 0.555 we read from the Z table, and I get 0.32. So the probability value, interval probability value is 0.32, which is nothing but 32%. Okay? And the answer is not 40% as we had naively computed, but the value is 32%. And that is more principle. We can answer why is it so, because the underlying distribution is log norm. Okay? And it would be foolish to ignore this knowledge, not to use this knowledge. In fact, we will be incorrect if we don't use this knowledge. Okay. So this was an example of interval estimate, and we learned how to make use of the probability standard normal probability table. Now we said that we can go backward, okay, by reading of these probability values and find out the number of cars which can be safely allowed on the bridge. So the bridge problem is indeed an example of multi-objective optimization. Okay, multi-objective optimization. There are many objectives which have to be satisfied: safety, utilization of facility, earning, people satisfaction, etc. And we have to satisfy ourselves that all these objectives are optimally satisfied. Now we would like to invoke probability. Let this number of cars be n, and each car's weight is normal with mean equal to 3 and sigma equal to 0.3. So we invoke here central limit theorem, and the central limit theorem, on which we'll have a lot of discussion, and we'll go back to the bridge problem when we discuss central limit theorem and its application. The sum of Gaussian random variables is Gaussian, okay, with mean and variance being sums of individual means and variances. So the sum of n random variables is normally distributed. This is the notation: tilde n mu, n mu as the mean, and sigma root n is the standard deviation. So the total weight of n cars is normal with mean as 3n and variance as n sigma square. So n into 0.03 square, which is n into 0.09. Okay, so this is the total weight, which is normally distributed. And the tolerance also is normally distributed with 400 as the mean and standard deviation as 40. Now the bridge becomes damaged when total weight exceeds the tolerance. And we're interested in finding the probability that the total weight will indeed exceed the tolerance. Okay? And we are interested in this probability. What is the probability that the total weight exceeds the tolerance? Okay, with value more than 0.1. Okay, what is the condition under which the probability that W total minus W tolerance is greater than 0, should be greater than 0 here, exceeds 0.1? So let n unsafe with that number, and we would like to make this statement intuitive. The intuition is that out of 1,000 cases of the bridge allowing n unsafe cars to pass over it, in more than 10 cases, the bridge will break. Okay, so this is the language equivalent statement of this probabilistic expression. I'm sorry, this value here should be W total minus W tolerance becoming greater than 0. Becoming greater than 0. Okay, let me make that right now. Yeah. Okay, so we're interested in the probability of W total exceeding W tolerance, and that probability being greater than 0.1. Okay, why 0.1? Because we want to see what is that n unsafe number where out of 1,000 cases of the bridge allowing n unsafe cars to pass over it, in more than 10 cases, the bridge will break. Okay, that is the language equivalent of the probabilistic expression. So now you can do some algebra. We are interested in this random variable W total minus W tolerance. Now W total minus W tolerance also is normally distributed, okay, by central limit theorem. Okay, we're invoking central limit theorem here. So the mean of this quantity and normally distributed quantity W total minus W tolerance, the mean of that will be 3n minus 400. This subtraction of the means. But the variances will be added. Okay, variances will be added because it is a square. So the standard deviation will be 0.09n plus 1600. 1600 is 40 square, which was given as the standard deviation of W tolerance. Okay, now we have entered the standard normal variable situation, and we want W total minus W tolerance to be greater than 0. W total minus W tolerance involves these quantities, W total minus W tolerance minus 3 and minus 400 divided by the standard deviation. So this quantity, I am just added this quantity on both left hand side and right hand side. And left hand side therefore can now become the standard normal variable. Right hand side becomes minus 3n minus 400. Okay, some simple algebra going on, and we want the probability of z to be greater than this quantity. Okay, and that probability should be greater than 0.1. I'm hurrying a bit because I'm towards the end of the lecture, but we'll go through this particular example, which is very instructive step by step. And when we solve this, we get n equal to 170. Okay, the solution is in this form. The probability greater than 0.1, okay, means the probability of a variable, the probability of z being greater than v being greater than 0.1 is equivalent to 1 minus probability of z less than v greater than 0.1. So we can do this algebra, and less than is important for us so that we can read off the z score table. So by reading the z score table and solving it, we get the value of z as 0.1 as 1.9. n equal to 117. So this is very systematic, straightforward solving of algebraic expressions leading to the value of n. So the point I was making here is that from the z-score table and from the interval probability, we can work backwards and get values of the quantities we are interested in. So bridge is a very good example of that particular situation. Okay, so we'll continue with the central limit theorem and coming back to the bridge problem, because there are many standard interesting points there. But I'll stop here and let me see if we have questions from the chat box. Okay. So in the chat box, hello sir, are such tables available for non-normal distributions as well from Aman? I don't think so, but I may be incorrect. I'll have to look for, I'll have to see more. Also, are different distributions interconvertible? Okay, that's a good question. So, yes. So, binomial distribution and Poisson distribution, they tend to normal distribution when n is large. The number of trials is large. So, binomial distribution tends to normal distribution when n is large, and n into p, okay, where p is the parameter, that is the mean of the normal distribution, mean of the normal distribution. Okay, so yes, standard distributions can tend to other distributions under conditions. Okay, from a moment to, it should be 0.34 and 0.3, not 0.32. Okay, that was the maybe the calculation mistake. How much to trust this? We calculated our empirical distribution using only 10. Oh, that's a very good question. So even if we have made use of the correct distribution, log normal distribution, but the number of samples was only 10. So very good question. So even if the underlying distribution is correct, doesn't the size of the distribution play an important role? Okay, so we'll have more things to say on this. Okay, we'll say more things. It's a very interesting point. So let me reserve the answer for discussion later. Okay, can we discuss hypothesis testing? We'll come to that. Actually, we are making progress towards that. How much? Okay, this was Nikhil. Okay, we are making progress towards that. From A to everyone, sir, is hypothesis testing significant for small sample space? This question is related to what Sapan was saying. How can you trust with only 10 samples? No, we'll talk more about this. Then from Prince to everyone, in real life scenario, how do we know the distribution beforehand? Oh yeah, so difficult. Okay, how do we know the distribution? For example, how did we know that the sand particle size follows log normal distribution? No, this is a lot of work. Okay, this is a lot of work and a lot of insight from people who deal with data. Okay, but one interesting point is that whatever be the distribution, the central limit theorem ensures that we can enter normal distribution under specific conditions and make use of theorems, tools obtained through normal distributions. Okay, so that is an important point which we will develop as we go along in the course, in the series of lectures. Is there any other question from anybody? Or any point?
Yes, sir. I had a question. Yeah, sorry.
Yeah.
So for an arbitrary distribution which does not have a Z table or a closed form CDF, what should be the best way to go about it?
Yes. So another form of another statement of central limit theorem comes into help here. So that version of central limit theorem says that if the sample size is more than 30, okay, if the sample size is more than 30,
Okay.
then if you take many, if you vary the sample, if you keep on taking samples, then the mean has a normal distribution. Okay, the mean has a standard has a normal distribution, and that mean slowly begins to go towards the mean of the population.
Okay.
Okay, and you can say that this mean, the random variable representing the mean minus the population mean divided by a particular sigma, okay, will take us to standard normal distribution. Now, you don't know population mean, you don't know population standard deviation, then what can you do? Okay, so we'll develop this theme gradually, but but the answer to your question, as well as to a point made by, I think, Sapan and others, is that whatever be the underlying distribution, if you sample enough and if your problem allows you dealing with sample mean,
Okay.
then you can make use of the machinery of the normal distribution.
Okay. So
But
our assumption is that in the absence of any knowledge, we assume that the data is normally distributed with the given mean and sample mean and the sample variance.
No, that's not what I said. Okay. If you don't know anything about the underlying distribution,
Mm.
then if you sample enough and the sample size is greater than 30,
Okay.
then, and if your problem allows working with the sample mean,
Okay.
then you are in the realm of normal distribution.
Oh, okay.
I'm saying that. Okay. So even if you don't know anything about the underlying normal distribution, central limit theorem gives you the machinery to remain within normal distribution and make use of that machinery. Okay. So that I'll develop slowly through CLT.
Sure.
Any other point? Okay. So if not, I'll sign off. The information extraction true group, we are meeting in about 5 minutes time from a Google Meet link.